With so many galaxies getting ripped apart or smashing into each other, you might think of our Milky Way as a comparatively peaceful place. Well, sorry about that, because it's actually a cannibal. We've seen evidence of the Milky Way devouring other galaxies before, and now it seems like we found another one. In this month's issue of the monthly notices of the Royal Astronomical Society, scientists announced evidence suggesting that 8 to 11 billion years ago, the Milky Way devoured a neighborhood they call the Sausage Galaxy. I mean, if you're gonna eat a galaxy, it might as well be a sausage galaxy. According to an international team of astronomers, some stars hanging out in the Milky Way's halo, a sort of spherical cloud full of stuff like old stars, serve as a record of this event, or more specifically, their orbits do. These orbits are super long and narrow, oriented radially with respect to the center of the Milky Way. These stars also have a noticeably different chemical makeup than other ones nearby, and the directions of their orbits go backwards, so the team concluded that they probably had to have come from a different galaxy. Since plots of these stars' velocities relative to others in the area look vaguely sausage-shaped, the team dubbed the stars Gaia Sausage, and the galaxy they came from, the Sausage Galaxy. It almost definitely didn't look like a sausage itself, though, although that would be awesome, because it would totally team up with that galaxy that looks like a fried egg. Anyway, just call me when they find a galaxy that looks like Pop-Tarts, I'll be there for that. When this galaxy collided with the Milky Way, it likely caused our disk to puff up, or it might have even broken part of it up and forced it to reform. Essentially, the sausage's guts got scattered around the whole inner Milky Way, adding to our galaxy's bulge. You know, when you have too many sausages. Telescopes like the Hubble have collected a lot of beautiful images of galactic collisions, but we don't have a time machine or a camera outside of the Milky Way to see them happen to us. So the team had to use computer models to check if the observed stellar positions and the trajectories could be produced by this hypothetical Milky Way sausage galaxy interaction. The simulations used data from both the Sloan Digital Sky Survey and the ESA's Gaia satellite, which is mapping stars in our galaxy and how they move through space. And they concluded that a galaxy roughly 5% the mass of the Milky Way with an extremely eccentric orbit could produce these leftover stars with weird orbits. Of course, this wasn't the first time the Milky Way ate another galaxy, and it won't be the last, but the sausage hypothetically contributed the bulk of the stars in the interstellar halo, which is a helpful thing to know about. In another paper, the team of astronomers also identified at least 8 globular clusters, which are dense spherical clusters of stars, that might have originally belonged to the sausage galaxy too. But since the paper hasn't completed the peer review process yet, we can't really say that for sure. Meanwhile, while the US was blasting off fireworks last week, another team was getting ready to share findings about different light shows on Jupiter. Specifically auroras, which happen when electrons get accelerated by Jupiter's magnetic field. The process is similar to how some auroras form on Earth, but on Jupiter, some of the planet's moons actually help shape what these shows look like. A study published last Thursday in the journal Science shed a little more light on the subject and also showed that these interactions are more complicated than we thought. Jupiter has upwards of 60 moons, but the most famous are those discovered by Galileo at the start of the 17th century: Io, Europa, Ganymede, and Callisto. All of them orbit within Jupiter's magnetosphere, or the region ruled by its magnetic field, and they're close enough to the planet that they form sort of an obstacle to any charged particles trying to follow Jupiter's super strong magnetic field lines. Basically, this causes a special kind of magnetic wave to form, called an Alvine wave. It accelerates electrons toward Jupiter's atmosphere and causes additional auroral emissions. This leaves a noticeable footprint in Jupiter's atmosphere, showing up as bright spots in both the north and south hemispheres. Astronomers have previously used the Hubble to study these features, but now that we have the Juno spacecraft orbiting Jupiter's poles, we have a much better vantage point. In this new paper, one team used Juno's Jovian Infrared Auroral Mapper, or GRAM, to reveal the hidden complexity within these footprints. In September 2017, GRAM set its sights on where models expected Io's footprint to show up. Since Io is the closest of the Galilean moons to Jupiter, it leaves the largest footprint. And one did show up there, but it was a lot more than just a big spot. Images revealed a trail of swirling vortices in both hemispheres, which sometimes split into 2 wing-shaped arcs. The main spot was located where models predicted, but secondary shadows stretched for 1,000 kilometers or so on each side, each about 1 Io diameter, away from each other. While the pattern is clearly something reminiscent of fluid dynamics, like air swirling off a plane wing, the team doesn't have a specific model that explains how Io's path through Jupiter's magnetic field creates it. They suggest the Alvine waves might be broken into smaller waves with different travel paths, which could lead to something so turbulent looking, but they're not positive yet. Still, the fact that something as small as Io can have such a big influence on Jupiter is pretty cool. The team also captured images of Ganymede's footprint, revealing never-before-seen double shadows of sorts, with two identical spots roughly 170 kilometers apart. This might be due to the fact that Ganymede is the only moon to have its own magnetic field, but again, more data would help. The good news is that Juno has at least another 3 years of work to do, so we'll have time to make more observations. And someday, we'll hopefully have a better idea of how Jupiter's magnetic field reacts to such a complex system. We've also observed Enceladus's auroral footprint on Saturn, so we know that this isn't something unique to Jupiter. In fact, these auroral footprints could be found where there's any electrically conducting moon orbiting inside a planet's magnetosphere, or even a planet inside a star's. So one day, we might look back on these Juno observations as a major step toward understanding a much bigger picture. Thanks for watching this episode of SciShow Space. Besides influencing Jupiter's auroras, it turns out that Io has a lot more to brag about, like the fact that it might have an underground magma ocean. You can find out all about that in an episode we did on Io.